Okay, so in the first four sections of this chapter, we've worked a lot in the details of both exponential and logarithmic functions, trying to get the basic principles down. So some of those sections are really loaded with content, like 4.3, 4.4, okay, and maybe 4.2 and 4.1 as well. So make sure you make yourself a good note page and go over those concepts. And now in 4.5, we're going to show some applications of exponential and logarithmic models is kind of what we're looking at here. So the first one we're going to look at, they group it together, exponential growth and decay models. And they come in this form here, right there. F of x equals a naught e to the kt. All right. So that's one form. Another form is a equals a naught e to the kt. So let me talk a little bit about the parts here. So remember, you might recognize this is kind of similar to the PERT formula for continuously compounded compound interest formulas or problems, and we used that before. A or f of x, oh, that should be f of t. Darn it, I'll have to fix that. That represents the amount after so much time, okay? So like when it was the amount in the account, but this time it's not going to be money necessarily. It could be how many people there are at a particular time, or how many cases of the flu there are, or something like that. Okay, so that is after time passes, after t, and t is going to represent time. Now, time could be measured in years or days or seconds. It just depends on the model. Now, we talked about a sub 0 or a naught. And I spelled this in another video and I misspelled it. It's not like that. A naught. Okay, so I looked it up. Okay, so it's the initial amount. So if you'll remember, it's the initial amount or the beginning amount, that'll help. What is K? Well, K is a constant, and we don't necessarily know that constant. We've had problems like that when we did the variation problems, right? It always gets a K, and we talked about that, and we found K. We're going to be doing some similar things here. Okay, so that's the formula. E, of course, well, that's the natural base, the natural number E, and we talked about that. So when do we use these exponential growth and decay models? Well, things like inflation, that's usually exponential. Interest, right? Compound interest. Populations are usually exponential populations. But you can have decay problems like radioactive material. It's decaying. And sometimes populations are not increasing, sometimes they're decreasing. That word says substance. Okay, so a radioactive substance. There's one more I was going to include. Oh, something like disease. Sometimes that grows exponentially. Or cells, when they're growing, they're multiplying and stuff. Sometimes those grow exponentially. Okay, so here's some information about the US population. And you can see here that in 1970, there were 203.3 million people in the United States. And it looks like it was growing. We know it's growing because as the years progress, as it gets later, as we have more time, we're getting a higher population. Okay, so then in 2020, it was at 331.0 million. Okay, so that's what this says. The graph shows the US population in millions for 6 selected years from 1970 through 2020. In 1970, the population was 203.3 million. Okay, so we got to have that piece of information. By 2020, it had grown to 331 million. Find an exponential growth function that models the data for 1970 through 2020. Okay, so we have to ask a couple things. When are we starting? We're starting in 1970. So let's get our model first. I'm going to put A equals A naught e to the kt. So our starting, we're starting, that's the initial, in 1970. And what was the population? So A naught is 203.3, and this is in millions. Okay, so that's A naught. What about 2020? Okay, so 2020 is going to be our ending amount. We're going to stop in 2020 because that's the information we have. So that's going to be our A, and that's going to be 331.0. Now, we don't know K. That's what we're looking for here. We don't know the constant. E, we don't have to worry about that. Time. How much time has passed? How many years are there from 1970 to 2020? Well, that would be 50 years, right? So 50 years. That's going to be the time, T. Okay, so we can put this all in the formula. This little A here just says it's letter A that I'm working on. Okay, our A, our capital A, is 331.0 if you like. And then A naught is 203.3. E to the K, we don't know K, but T is 50. And remember, that's all in the exponent. So problems like this might look familiar. We've done similar things when we were doing compound interest. Okay, how do we solve for K? First, you have to divide by the 203.3. You have to isolate the exponential part. So this goes from the last section we were talking about solving equations. Okay, so those cancel, and I have 331 over 203.3. I'm going to leave it that way. E to the, and I'm going to make this 50K. I'm trying to solve for K. Now, because it is base E, we're going to take the logarithm of both sides, but we're going to take the natural log of both sides. So sometimes my students say natural log it, like you're going to just take the natural log on both sides. We'll have to make sure we have parentheses around our division there. And then we have the natural log of e to the 50k. All right, so on the right-hand side, this is the left-hand side, nothing happening there right now. Now, I'm not going to divide that out and round it off. I'm going to wait till the end and get the most accurate number I can. On the right-hand side, though, this is property 3. It says when the base here is the same as the base in the argument, it just equals 50k. Well, now how do you solve for k? Divide by 50. So in our calculator, we want to type the natural log. You're going to have to use natural log. 3 parenthesis 331.0 divided by 203.3. Close that parenthesis. That's really important. And then divide it by 50. And we're going to get a decimal approximation. And we're going to go 2 decimal places. So stop the video and calculate that and then come back. Okay, when I come back, I have 0.009748 on my calculator, but 2 decimal places is going to be 0.01. Okay, so now we know what K is. That's what we were figuring out. This is K. Remember, those canceled. Okay, so that's K. Now we can write the formula. A equals A naught e to the, we're going to put 0.01 t. And now they can ask us something. What do they ask us in part B? B. By which year will the U.S. population reach 400 million? So this time we're looking for T. By which year? That's going to be the T. And then this 400 million, that's going to be the A. That's the end amount we want. So 400 is going to equal, now A naught didn't change, so it's 203.3. E to the 0.01 t. And you'll notice this is very similar. The solving is going to be very similar to what we just did. It's kind of like, well, just different numbers. So we're dividing by 203.3. Those cancel. And then I have 400 over 203.3 equals e to the 0.01 t. Now you're going to natural log it. So you're going to go natural log here and natural log here. Okay? So save a little writing here. So I have the natural log of 400 divided by 203.3, close that parenthesis, equals, and remember it's just going to equal that exponent, 0.01t. Divide by 0.01, divide by 0.01, and then I'll have to put all of that in the calculator, and I'll get t to be something. T is going to equal, and I'm going to round off to the nearest year. So stop the video and do the calculation. Okay, so I get 67.678, so that's going to be about 68 years. Now, do they want to know how long it takes or which year that's going to be? Which year, by which year? Okay, so in 60 years, we started in 1970, right? So we're going to have to add 68 years to that. And we're getting, so in the year 2038, that is when we're expecting the population to be 400 million, right? 400 million, I think. Yeah. Okay, sorry about all the scrolling. There you go.